Okay, so I'm going to go over some problems related to electrostatic forces. So, first of all, the first problem, Robert Millikan received a Nobel Prize for determining the charge on the electron. To do this, he set up a potential difference between two horizontal parallel metal plates. He then sprayed drops of oil between the plates and adjusted the potential difference until drops of a certain size remained suspended at rest between the plates, as shown to the right. Suppose that when the potential difference between the plates is adjusted until the electric field is 10,000 newtons per coulomb downward, a certain drop with a mass of 3.27 times 10 to the negative 16 kilograms remains suspended. Okay, so we know that the electric field, which is Q, is equal to 10,000 N per C, and we know that the mass is equal to 3.27 times 10 to the negative 16th kilograms. So, and we also know that since it's on Earth, the acceleration due to gravity, or g, is equal to about 10. So, knowing all of this, we need to find the magnitude of the charge. And since we know the electric field, the mass of the drop, and the gravitational force, and we're trying to find the magnitude of the charge, we can use the equation EQ equals mass times gravitation. Okay, so if we draw the free body if we draw the free body diagram of this situation, we have that this is the mass, the weight, which is the mass times acceleration of gravity. And we also, since it's suspended, there is an equal force in the opposite way that's equal to EQ. So, knowing this, we can set the two equal to each other. We have EQ equals mg. So, now we just plug in what we know, and so we get, or we're solving for Q, so we can have Q equals mg over E. And if we plug in what we know, then we get Q equals 3.27 times 10 to the negative 16th times 10 over, this is actually, nope, that's right, that's Q, and, or wait, hang on, this is actually E, it's the electric field, my bad. So, this is 10,000 newtons per coulomb. So, simplify that and you get that the answer is 3.27 times 10 to the negative 11, and that's what the magnitude of the charge is on this drop. So, now if the drop slowly evaporates but the charge remains the same, so Q remains the same, what happens to the drop? Does it go up? Does it go down? Does it stay the same? So, if we draw this again in the free body diagram, so this is the drop, and this is mg, or EQ stays the same, because it's the same charge, but since the drop is evaporating, it's losing mass, so the mg becomes smaller, and the forces are unbalanced, and with EQ being the stronger force, so the drop moves up. Okay. Next. So, a proton travels at 3.0 times 10 to the 6 meters per second at an angle of 30 degrees. it's traveling at 30 degrees to the direction of the magnetic field, and the magnetic field has a charge of, so the magnetic field, which is B, is 0.3 T in the y plus direction. So, first we're going to try to find the magnitude of the magnetic force. So, since we know the velocity and the magnetic field, and we know the charge, we can find the force with the equation F equals QVB. Now, you might be wondering where we find the charge since it wasn't given to us in the problem, but it actually was given to us in the problem because it mentions, because you're dealing with a proton, and a proton has a charge, and the proton's charge, Q of a proton, is 1.6 times 10 to the negative 11. So, now we have all that we need to plug into this equation and find the force. So, force is equal to Q, which is 1.6 times 10 to the negative 11, times velocity, which is 3.0 times 10 to the 6th, times B, which is 0.3 T. However, in order for this to work, you have to, so the direction of the proton is moving in has to be perpendicular to the magnetic field in order to multiply it. And since it's not, we have to find a way to make it that way. So this is the way that the magnetic field is going, and this is the way that the direction that the proton is traveling. So, and this is 30 degrees. So we're trying to find what x is. And in order to find x, you can just use sine 30 degrees. And then, so you multiply this by sine 30. And so, that's all you have to do. So when you multiply it out, you get that the force is equal to negative 1.422 times 10 to the negative 5th. Okay. Next, we are going to find the acceleration of the proton. And in order to do this, we can use the equation F equals ma, force equals mass times acceleration, which is derives from Newton's second law of motion. So we know from the previous problem that F is equal to negative 1.422 times 10 to the negative 5th. And we know that the mass of a proton is 1.67 times 10 to the negative 27th. So we plug this into the equation. And okay, so we're solving for the acceleration. So we have force over mass is equal to the acceleration. So we have negative 1.422 times 10 to the negative 5th over 1.67 times 10 to the negative 27th is equal to acceleration. And that ends up being negative 8.5 times 10 to the 21st is the acceleration. Okay. So, next problem, we have that a sodium ion, Na+, is moving at velocity is equal to 0.851 meters per second through the bloodstream of a man near a large magnet, through the bloodstream of a man's arm near a large magnet. The magnetic field has a force of 0.254 T, and it's moving at an angle of 51 degrees to the arm, or to the motion of the eye. the ions are moving at an angle of 51 degrees to the magnetic field. And the arm contains 100 centimeters cubed of blood with 3 times 10 to the 20th Na plus ions per cubic centimeter. So so again, we're going to be using the equation F equals QVB. So we know that Q is just equal to 1 since the charge of the sodium ion is positive 1. And we know that the velocity, we know B, and so we just get that F equals 1 times 0.851 times 0.254. And then, again, since it's moving at an angle, you have to multiply it by sine 51 degrees. So you get that the force is equal to 0.145. Okay. But since the force is only acting, this is the force for only one sodium ion, we have to multiply it by the number of sodium particles that are in the bloodstream. And so since there are 100 centimeters of blood and 3 times 10 to the 20th per cubic centimeter, you just simply multiply it across, and you get that there are 3 times 10 to the 22nd sodium ions in the arm, and we multiply that by the force per one ion, 145, equals 4.35 times 10 to the 21st as the force newtons.